This is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we go through simultaneous equations. Now, simultaneous means at the same time. So we are looking at a system that has many equations and many variables, and we want to come up with a solution that solves each equation at the same time. You're probably familiar with situations in which we have two equations and two variables. So let's start by looking at them. So let's look at an example like this. So we have two equations, x plus y equals 8 and 2x plus y equals 13. We have two equations and two variables, the two variables being x and y. So for the purpose of this video, we're just going to look at situations where the number of equations is the same as the number of variables. So you probably know by now that both of these equations are linear equations. We're doing linear algebra. So I could actually graph each of these equations in the Cartesian plane. I could graph this one and this one. Each would be a straight line in the Cartesian plane. So it turns out that these two lines would intersect. They'd hit each other once and only once. So that would be at the point 5, 3. So that's a solution to both equations at the same time. If I substitute x for 5 and y for 3, remember x is always written first, then I would solve both equations at the same time. Mathematicians, when they have a solution, aren't satisfied. We're a picky bunch. We also want to know, are there any other solutions? In other words, is this solution unique? So it turns out, for these two equations, it is unique. Because if I graph each of the lines, they will intersect once and only once at this point, 5, 3. There are no other solutions. There are no other sets of values for x and y that will make both equations true at the same time. So this is an example of a system of simultaneous equations that has a unique solution. And most of the time, when you have n equations and n variables, the number of variables is equal to the number of equations, you get a unique solution. But when we're dealing with systems of linear equations, there are two other possibilities. I can have infinitely many solutions, or I can have no solutions at all. Let's look at examples of them. So I said before that if you have a linear equation, you can see it as a line in the Cartesian plane. So if I have, and I'll stick to an example of two equations, two variables, if I have two equations and two lines, how could there be infinitely many solutions? So remember, a solution is where they intersect. So two lines can intersect infinitely many times if they are in fact the same line. So if I have the equation, say, x plus y equals 8, and I have a second equation, 2x plus 2y equals 16. In fact, there are infinitely many solutions to these equations. So why is that? Well, it's sort of like I only have one equation, because this equation, the second one, is equivalent to the first equation. So I'm not really adding any additional information. If x plus y equals 8, then 2x plus 2y must equal 16. That really doesn't give me any additional information. I could have, x equals 5, y equals 3. That's a solution to both equations. But I could also have solutions like x equals 4, y equals 4, x equals minus 7, y equals 15. All of these are examples of solutions to both equations. If I were to graph both of these lines, they would lie on top of each other because they are the same line. So they would have infinitely many solutions when they're the same line. So again, looking at an example of two equations, two variables, what would it mean if there were no solutions? Remember, each equation is a line. The solution is the point of intersection. So two lines don't intersect if they're parallel. So if I have something like x plus y equals 8 and say 2x plus 2y equals 15, I have something that is inconsistent. and that's why there are no solutions. So what do I mean by inconsistent? Well, if x plus y equals 8, 2x plus 2y must equal 16. But this is telling me it's 15. It's saying 1 times something is 8, but 2 times that something is 15. They don't make sense. They're mutually exclusive. If the first one is true, the second one is not true, and vice versa. So any solution to the first equation, like 5, 3, will not be an equation to the second equation. So it is impossible to solve both of these equations at the same time. Now, again, I told you I'm only looking at situations in which the number of variables is equal to the number of equations. It turns out it doesn't matter whether you have 4 equations and 4 variables or 10 equations and 10 variables. These are the 3 possibilities if the equations are linear. You can have a unique solution, so one and only one solution. You can have infinitely many solutions, or you can have an inconsistent system, meaning there are no solutions. So when we get to solving simultaneous equations with more than 2 variables, they become really hard to do algebraically. But matrices actually assist with that. So how do we set up the matrices? Well, what we do is we create an augmented matrix. So on one side of the matrix, you have the coefficients. So the matrix of coefficients is set up as follows. So each row is a different equation. So we had 2 equations, we'll have 2 rows. And each of the columns is a different variable. So again, we had 2 variables. So we're going to have 2 columns in the coefficient matrix. So we just put the coefficients in. So here, x plus y equals 8. The coefficient of each is 1. In the second equation, the coefficient of x is 2, and the coefficient of y is 1. And over the other side of the augmented matrix, we put the 2 answers to the equations 8 and 13. That's how you set up a coefficient matrix. So again, each row is a different equation, each column is a different variable. So this column is the x coefficients, the y coefficients, and this is first equation, second equation. So what you do is you use what we learned in the previous lesson. You use row reduction and you keep going until what we want to get is something like this. So it turns out if you follow row reduction here, you get something that looks like this. You get an easier system to solve. So when we get a matrix that looks like this, we have 1x is equal to 5, so x equals 5, 1y is equal to 3. That's what we're aiming for. We want a 1 in each column and each row, but we want that 1, the leading entry, to be the only entry in each row and column, because then we can find the solutions very easily. So what I'm going to do as quickly as I can is I'm going to give you one example of each of the 3 cases of what the matrices look like. So let's look at these 3 equations here. We have 3 equations and 3 variables. So let's set up our augmented matrix. So remember, each of these rows, there'll be 3 of them because each represents an equation, a different equation. And remember, the columns represent different variables. So again, there's 3 of them. So x, y, and z are the 3 variables. So on the left-hand side, we just put the coefficients. So the first equation, the coefficients are all 1. Second equation, x, no y, so it's coefficient 0, and the coefficient of z is -1. And similarly in the third one, it goes 1, -2, 0, and we put the 3 answers on the right-hand side. So what I do is I reduce this matrix using Gaussian elimination, or row reduction as we've called it, and I want to reduce it so this matrix becomes as close as possible to the identity matrix. So let's go ahead and perform those operations. So to start with, I want to, because I have a 1 here already, I want to make this one here 0. And I want to make this one here 0. So I can achieve both of those by subtracting the first row from each of the relevant rows. So row 1 is going to stay the same. Row 2 I'm going to take it and subtract row 1, and I'm going to do the same for row 3. And so I keep performing row operations. Remember, I want to go sort of in this direction. I keep performing that until it's in reduced row echelon form. So I keep going along these lines until it's as close as possible to the identity matrix. So if I keep going, I end up with this matrix down the bottom here. So that means I have solved the equation. I have 1 lot of x equals 6, 1 lot of y equals 2, and 1 lot of z equals 1. So the point here is we're just continually changing this system into something that's equivalent, that has the same set of solutions, but easier to deal with. So now let's look at an example of a set of equations that has infinitely many solutions. So let's look at this system of equations here. It will turn out that it will have infinitely many solutions. As I sort of showed you on the previous slide, or 2 slides ago, that happens when one of the equations doesn't really give you any additional information. So it might not be easy for you to see, but this third equation is actually just the first 2 added together. So it really doesn't add any information. Of course, anything that solves the first 2 will also solve the third. So it's sort of like we only have 2 equations and 3 variables, which is problematic. So that's intuitively why we're going to get infinitely many solutions. Let's look at what happens when we try to use row reduction. So we set up our coefficient matrix as we did in the previous examples. Each row is one of the equations, each column one of the variables. So now let's try to row reduce this. Again, we don't need to worry about this 1 here because that's what I want. I want it to be 1. So I start by changing this one and this one to 0. So now what I've done is I've subtracted 2 lots of row 1 from row 2 and subtracted 3 lots of row 1 from row 3. So I'm just using the normal row operations, but it turns out I've now got 2 rows that are exactly the same. So if I were to do another step, I want to make this 0, what I would do is I would take row 3 and I would subtract row 2. So what will happen is row 1 stays the same, row 2 stays the same, but row 3 ends up being a row of zeros. And that's what happens when there's not one and only one solution. When there's a problem, you get a row of all zeros. So this one here, we can't really do anything more with it. We can't really go on with our row reduction algorithm. There's no point. We have the situation where 0x plus 0y plus 0z equals 0. And of course, there are infinitely many solutions to that equation. So when we have all row of zeros, including this one here in the solution, that's when we can stop and say there are infinitely many solutions, okay? What it actually means is there is what we call a free variable. So what I mean is if I actually want to find a solution to this system, what I need to do is I need to first choose what one of the variables is going to be. And I can choose it to be anything. I can choose z to be anything. I can choose it to be 1 or 2 or 3 or whatever. And each time I choose a different value of z, I'll get a different solution for x and y. So here, there is one free variable. Now, it actually doesn't matter whether you consider x the free variable or y or z. I'm just considering it z because z is the only one. This is sort of the only column, the z column, that doesn't have a leading entry. So the free variable turns out to be equal to the number of rows of 0. Or as I said, it's equal to, say, the number of variables that don't have a leading entry when you reduce the matrix. So here there is one free variable because there is one row of zeros. All right, finally, let's look at an example where I try to solve a system of simultaneous equation, but there are no solutions. Let's look at this system here. So it's not at all obvious just from looking at it that it would have no solution. Things are so easy when we have two equations and two variables. We only need to check if the coefficients in one equation are scalar multiples of the coefficient in the other equation. That's when we'll either have infinitely many or no solutions. But here it's a lot more complicated. It turns out that this has no solution because the coefficients here are just double the coefficients in this one plus the coefficient in this one, right? But that's not obvious at all just from looking at it. But it turns out that this number here, 15, is not twice this plus this. So it's inconsistent. What I've sort of done is I have taken 2 times the first equation and added it to the second equation. So then this number would need to be 2 times 4 plus 6, which it isn't. So that's the intuition as to why there are no solutions. But let's once again look at what will happen if I try and solve this with Gaussian elimination or row reduction. So, of course, in this one, instead of calling the variables x, y, and z, I've just called them x1, x2, and x3. It doesn't really matter what you call them. So, again, each gets its own column, and each row is a different equation. So, the first equation will be 2, 3, minus 1, 4. The second one has no x1 coefficient, and there'll be 2, minus 1, 6, and so on. I'm sure you know how to do this by now. So let's try and use row reduction. So first off, we have to make this into a 1. So what you see now, in addition to changing the first entry to 1, I changed the 3, 1 entry to 0, as I'm supposed to do during row reduction. Now you can see we have 2 rows that are sort of the same, this row and this row, but the problem is this number and this number are not the same. So if I go ahead and do another step of row reduction, remember I now want to make this into a 0, I can do that by leaving the first row alone, leaving the second row alone, but I'll take row 3 and I will subtract row 2. So I get rows of 0 here, 0, 0, 0, but 7 minus 6 is 1. What I've actually done is I've taken my original system of equations here and I've reduced it into something that's equivalent. But it's equivalent, the third equation, to 0x1 plus 0x2 plus 0x3 is equal to 1. But that is inconsistent in and of itself. That doesn't make any sense. You can't times any number by 0 plus any number times 0 plus any number times 0 and get 1. You're adding up heaps of zeros and getting 1. That doesn't make sense. That has no solution. It is inconsistent. So we don't need to worry about free variables or anything here. There is just no solution because any solution to these 3 equations would have to satisfy 0x1 plus 0x2 plus 0x3 equals 1. There is nothing in the world that satisfies that. So what is the difference between infinitely many solutions and no solution in terms of the row-reduced matrix? Well, it is we get a row of zeros in the coefficient matrix for both of those cases. If we have that row of zeros, if this number here is 0, there are infinitely many solutions, as in the previous example. But if it's not 0, the system is inconsistent and there is no solution, as happened here. Alright, sorry for the long video. This has been the luckiest maths teacher in the world. Have a great day.